All right, greetings everyone. Welcome to the fourth part of the video for section 8.1. Moving into kind of the second part of 8.1, where we're going to talk about a new set of formulas that we can use to find information in non-right triangles. So first thing I want us to look at is whether or not we can always use the law of sines, because we did say it works for non-right triangles, but does it help us find information in any non-right triangle? Let's take a look at this. So here it looks like someone has measured a point out from a pond out here that's about 800 feet from one end of the pond, 900 feet from another, and then we see that there's a 7-degree angle in between those two sides. And let's say we were interested in finding the length of this opposite side here, which I'm going to call A. Well, if we try to use the law of sines here, what we would do is do the sine of the angle opposite the side A, which is 70 degrees, over A equals, then we can choose another one of the sides, like say this 900-foot one. So we do 900 feet under, but we need the measure of the opposite angle. And notice that in this case, we don't know what that is. Right? And so now what we've got in our formula here are two different variables. And so we can't solve that. And we'd run into a similar problem if we tried to use the side of length 800 feet. So crap, what are we going to do? Well, as I mentioned, we need another formula. And what we're going to do here is we're going to again derive this formula. Now, this is not something I would expect you to do on a quest or a project. But as I mentioned in one of my previous videos, I think it's important to know about where formulas come from and know they don't just drop out of the sky, even though it may seem like it sometimes. So what I'm going to do is draw a triangle over here. And I'm going to label the sides, label this one B, this one C, and this one A. And then I'm also going to label the angle opposite of A as alpha. All right. And then in this triangle, I'm going to drop down an altitude. So right here, so height of the triangle that intersects this bottom side at a right angle. And I'm going to call that side H there. And then this side adjacent to the angle of alpha, there in this smaller right triangle, I'm going to call that X. Which if we do that, then we know that over here on this right-hand side, that length there would be C, have a length of C minus X. And the reason we know that is because the entire length of this side is C. And if we take away X, which is this length, so we do C minus X, what we'll be left with is the pink length here. Okay, so that's C minus X. All right, now the next thing I want to do is use the Pythagorean theorem to set up some formulas in each of these triangles. So first of all, notice in the left-hand right triangle here, we've got a side of length X, side of length H, and the hypotenuse is length B. So we know that the Pythagorean theorem there will tell us that X squared plus H squared equals B squared. And I'm sorry, that might be hard to read. Let me use a different picture or color. So again, we have X squared plus H squared equals B squared. And then in the other triangle, the other right triangle here, again, we have a side of length C minus X, a side of length H, and then A is the length of the hypotenuse. So in that case, we would have C minus X quantity squared plus H squared equals the length of the hypotenuse, which is A squared. Okay? So we end up with something like this. Now, one other thing I'm going to do kind of off to the side here is look at in that first right triangle we were looking at, the one on the left there, what the cosine of alpha would be. Remember that a ratio for cosine is adjacent over hypotenuse. So in relation to the angle alpha, x would be the adjacent side, b is the hypotenuse, length of the hypotenuse. So our ratio here would look like x over b. And then for reasons that'll become clear here shortly, I'm going to solve for x here, so I'll multiply by b on both sides. These cancel out. So I have x equals, but not that, sorry. X equals b times cosine of alpha. Okay, and I'm just going to kind of keep that off to the side for now. All right, now going back to these other two equations we have up here in the upper right, we have the x squared plus h squared equals b squared, and the other one. In the x squared plus h squared equals b squared, I'm actually going to isolate the h squared. So I'm going to do that by subtracting x squared from both sides. When we do that, we end up with h squared equals b squared minus x squared. And now we have h squared equals this. And so that means that this right here, this b squared minus x squared, can be substituted for the value of h squared because we have the h squared equals that. So what I'm going to do is over here in the other equation, again, sorry for the freak out by the computer, over here, I'm going to input this expression for h squared. So what this equation can now become is c minus x quantity squared plus what we have here, the b squared minus x squared. And then we have that all equals a squared. Okay. And then the math of magic will continue from there. So I'm going to erase this for now. And what I'm going to do next is deal with this c minus x squared. So I'm going to FOIL that out, which as an aside, recall that to FOIL that, or really to multiply this, we need to do c minus x times c minus x, which requires FOIL. And so when we do that, we'll end up with c squared minus 2 cx plus x squared. So you can double check me on that. Plus b squared minus x squared equals a squared. And notice here then we have a minus x squared and a plus x squared here. We can cancel those out. I'm going to rewrite the left-hand side in alphabetical order. So I'm going to put the plus b squared first, add the c squared, and then minus 2cx equals a squared. And then we were actually almost done here because recall that back here in this original triangle, before I added in the x's and the h's, all we had were side lengths of a, b, and c, right? And x was something I added in. So in this formula we're building, we're going to want to get rid of the x. Well, the way we can do that is using this equation we have right here, what x is equal to. So it's equal to b times cosine of alpha. So we can substitute that in as b squared plus c squared minus 2 times c. Instead of x, I'll put times b cosine alpha equals a squared. And if I just rewrite this a little bit, make this a squared equals b squared plus c squared minus 2, and I'm going to do this in alphabetical order, bc times cosine of alpha. Well, there we go. There's one of our renditions of the law of cosines. Isn't that fun? Yeah, it is. Now, hopefully you see that it's called the law of cosines because it contains a cosine in it. All right, so again, all of this was just to understand where this formula comes from. And so here's the more general version of it. So you'll see up here, we have again the a squared equals c squared plus b squared minus 2bc cosine alpha. And then you see different combinations down below. Now, what I want us to notice is for the one that we did, notice that it has the a squared by itself over here, which here's the side length of a. And then on the right-hand side, we have C's and B's together, and we have C and B here. And then it also includes the alpha. So notice what the setup here is, that on that right-hand side of the equation, we have two sides and the included angle in them that's all together on the right-hand side. Okay, so I point that out to say that one way to remember the law of cosines, again, you don't have to memorize all three of these formulas. It's more of a format that it's the side squared here is equal to the sum of the squares of the two other sides minus 2 times the length of those sides times the cosine of the angle across from there, right? So in the formula for a squared, we have a cosine of alpha because alpha is the angle across from the a, okay? And you could check that a similar pattern is followed for these other two. The other thing I want you to know or notice is that if we were to kind of ignore all of these parts right here of these triangles, or these formulas, excuse me, hopefully you would agree that these parts of the formulas all look kind of like the Pythagorean theorem, right? But of course, they do include these other parts, so they're not exactly the Pythagorean theorem. And another way we can kind of think about them is like the Pythagorean theorem with a little bit of an adjustment, right? This part being subtracted at the end here could be like an adjustment. And so the law of cosines is really kind of like our version of the Pythagorean theorem for triangles that are not right triangles. We have to add that little adjustment at the end for them not being right triangles. All right, so let's go back to our pond problem here. So we're still trying to find that length across the pond there. Again, I will call that A. And we'll notice that in our setup here, we have kind of that setup we were just looking at, right? We've got a side alone here. We have two sides and the included angle. And so these in this, for example, could be our B and our C, and the 70 degrees here could be our alpha. So if we want to solve for the value of A there, we could set this up using that A squared equals B squared plus C squared minus 2 times B times C times cosine of alpha. Plug in all the information we have. So A squared equals, let's see, 900 squared plus 800 squared minus 2 times 900 times 800 times cosine of 70 degrees. And we work that out. Let's see, plug all that stuff in the calculator on the right-hand side all together. I think I get 957,490.994. We can solve for A by taking the square root on each side. And when we do that, I believe we end up with A equals 978.5, and I can't read my own handwriting. 515. And of course, we're talking about feet here. Okay, so that's our law of cosines. Cool. Thank you for watching.